For biomaterials and biomechanics, this is more of a biomaterials talk. There's usually 2 or 3 questions on the OITE every year. I kept track of them and did all of the OITE questions when I was a resident, and then I think I've kept up with it since then. So I think all of the questions on OrthoBullets for the OITE can be answered off this piece of paper. If you guys know of one, that is not answerable by this piece of paper, just let me know and we can add it to it. The goal of this is not to make you a materials property expert by any means. It's for you to be able to get another, 1 or 2 questions right in each of the sections. So hopefully, if they ask you any materials properties questions on the boards or the OITE, if you know everything on this page, hopefully you should be in good shape. So in general terms, just starting at the top of that page, there's a difference between elastic and plastic deformation. David, you talked earlier, just in 2 sentences, give me the difference between elastic and plastic deformation.
Just reversible versus irreversible. So elastic would be reversible deformation, and then plastic deformation would be irreversible, so the material does not return.
Right. So like if you have a knife or something plastic and you load it and then you release the load and it goes back to its normal shape, that's elastic. What's the point called? This might be brittle, but what's the point called that if I were to go past it, it would not return to its initial shape? Oops, that was brittle.
Yield point.
The yield point, right. They've never asked this, but on the stress strain diagram, let me see here, green. Mechanics on 1 page, share. So on the stress strain diagram, for a brittle material, which is what I just showed you guys, the yield limit, or the yield point where it undergoes the transition from elastic to plastic deformation, is very close to the ultimate strength of the breaking strength, right? It's really hard to take a plastic fork or a plastic knife and get it to bend without breaking. Does that make any sense? Yeah, it's hard to do. It would have done it had I stopped, but what sorts of, so that's a brittle material, whereas the yield limit is very close to the ultimate strength. What are some, what's the classic couple orthopedic materials that are brittle? Tyler Tetro.
Tyler was talking to the CSI rep.
Oh, sorry. Somebody else.
Ceramics?
Yep, ceramics is one. And there's another one that they typically say.
PMMA?
Yep. So basically, those are things that basically shatter. Like if you think of something that's brittle, like if you drop a plate on the floor, anything ceramic, anything made out of glass is a brittle material, which is in contrast to a ductile material, which is most metals. So if I were to take a metal rather than a plastic knife, if I were to take a metal knife, I would be able to bend that and make it bend and then let it go and it would stay bent after it reached the yield point. They've never asked this before, so this is this red line here for a ductile material. What if you stop right here and let it go? Can you see my cursor?
Yep.
Yeah, okay. So if you get to this point on the yield curve and then let it go, it just follows that exact same curve back down and then doesn't have any residual strain or any residual set. What happens if you take it past the yield point and it begins to plastically deform? And let's say you get to here and you let the load go, you release the stress that you've applied to it. How does that behave? What curve does it follow to get back? Casey. Is Casey there?
I'm very sorry. I think my internet connection today is faulty. Can you point with your cursor one more time?
So if you have a duct, I just call on you. Anybody can answer, but if you have a ductile material and you come up to here on the stress strain curve and then let the stress off, it follows that same stress strain curve and goes back to zero. So there's no plastic deformation. If, let's say, you go past the yield point and you're deforming the material plastically, and then you let the stress go, how does that get back to zero, or does it get back to zero? How does it get back? Does it do that? Does it unbend and then follow that? It comes straight back.
Sorry, I don't think I can see your cursor, but I know your question. And if you go past the yield point, then you're in the plastic deformation zone, and so it will not return back to its original shape.
Correct. And like the thing that they've never asked, but I think they could possibly, is if you go past the yield point and you let the stress off, it doesn't follow that red line back to zero, because that would get you back to zero. Basically what it does is when you let it go, it follows a different line that parallels the slope of the linear region of the stress strain curve. So if you could like start here, like I said, I don't know if you can see my cursor, but if you would go to anywhere on that plastic deformation part and then draw a line parallel to the linear portion of it, that will get you back, and you follow that back down to the x-axis. That amount of strain is whatever your residual strain is. So if you bend that knife, or if you bend that piece of metal to a certain amount and then let the stress off, it will recover some. It will recover the amount that it took to get to the yield point, but then the amount that it continues to be residually deformed, if you drew a line that's parallel to the elastic or to the linear version, that would get you back down to the strain axis. That's what its residual deformation is. And again, they've never asked that, but I think they possibly could. And then ductile materials just continue along, plastically deforming. They get to their ultimate strength, which is the maximum stress, and then they keep yielding, and then they get to their breaking point. But it's a much longer and more drawn out cycle than for a brittle material like that knife that I broke. The other thing they like to talk about is viscoelasticity. And all the questions they're going to ask you on the OITE or boards is just a vocabulary test. So if you guys know the definitions to all the words, it's very little interpretation on your own. It's basically knowing the definitions of words. So it's a one big vocab test. Who else is over there? Who's Brady?
Yeah.
I don't know Brady. Brady, are you an intern?
Yes.
Awesome. If somebody were to ask you, this might be unfair for an intern, but if somebody were to ask you to explain to them what viscoelasticity is, or what viscoelastic materials are, what would you say?
I guess it has both viscous and elastic materials, and it depends on the rate of loading.
Rate is the key word. So you're right. It has viscous. So viscosity implies some time. Anytime you have time or a rate of application, that's viscoelasticity. So if you notice on these stress strain diagrams, the two big ones on that piece of paper, there's no time on either of those. Neither of those is the time axis, right?
No.
So neither of those types of materials are dependent on the rate of application, the rate of stress or strain application. So like metals, ceramics, PMMA, all of that stuff, we think of as, in engineering terms, they call it Newtonian, but it doesn't matter how quickly you bend the metal, it just matters with how much force you apply it, which is different than most biological tissues, bone, tendons, ligaments. It doesn't just depend on how much stress you place on them or how much strain you place on them. It also depends on how fast you apply that strain. In a real world practical example, that's why you see a lot of avulsion type fractures in kids. It's usually from like eccentric loading, or when people get quad or patellar tendon ruptures. When you have an eccentric load, that's usually a very fast rate of strain application. Like somebody fell off a curb and twisted their ankle and they'll get an avulsion fracture off the base of their fifth metatarsal. The reason that is because ligaments, when you apply a strain or a stress very quickly, they are very stiff. And if you apply that same strain over more time, their modulus of elasticity or their stiffness is much less. So if you apply it quick, like you fall off a curb, That same amount of stress can cause an avulsion fracture. The tendon is really stiff and it just pulls off a piece of bone. Whereas if you apply it slowly, like if you're just stretching, right, from a slow stretch, you can, you know, that's the whole goal, is to not get injured by applying stresses more slowly. The modulus of elasticity is, how would you describe that to somebody, Chase? Chase isn't here.
It's basically the stiffness,
Oh, say that again.
essentially the stiffness.
It is. The modulus of elasticity is the stiffness, also called Young's modulus. Graphically, how would you represent that on the
Slope of the stress strain curve
Yep, particularly in which part?
in the elastic zone.
Yep, in the linear zone, right. So if I can get back to this again. So yeah, Young's modulus of elasticity, is the slope of the stress strain curve in the linear region. They also like to ask about this. Casey drew it up on the board a couple weeks ago, I think, in fracture conference. For biomaterials, tendons, ligaments, stuff like this, they have what's called the toe region. Can you explain that to everybody again, Casey? I know I've called on you twice already.
Yeah, the toe region is the area where the fibers are not at their maximal length yet, and so they have an uncrumping phase before they start reaching the elastic zone.
Exactly right. So all of the little collagen fibrils are kind of disorganized. So in the first part of the stress strain curve, like for a ligament, it's not very stiff. You can see the slope of the stress strain curve is very shallow. So it's not very stiff until all of those collagen fibrils line up or align. And then once those collagen fibrils align and you continue to apply the load, then it approaches, or then it gets into the linear region of the stress strain curve. Most non-biomaterials don't have a toe region. So that's something that's fairly unique to biologic materials. Like metals don't have that, you know, ceramics, all this, the non-biological materials don't have a toe region because they don't have those little collagen fibrils that need to get uncrimped. There was a question several years ago about what finite element analysis is. It's basically breaking up a complex shape into much smaller and simpler shapes. And if you can remember back from like high school or college physics, you can do free body diagrams to figure out the resultant accelerations or deformations on different bodies. Basically, they take a very complex thing, they break it up into much simpler things, and then each part they balance the forces as well as the moments around each of the little smaller, they usually do trapezoids or triangles or some sort of polyhedrons, but it's basically a way to break up a more complex shape into simpler things and then balance all of the stresses and moments about each one. There was a question on that long ago. So now that you've seen what the definition of finite element analysis is for orthopedic surgeons, hopefully you'll be able to click on it and get it right. What else did we talk about? At the bottom of that page, we talked a little bit about viscoelasticity. The two buzzwords they will ask you about in viscoelasticity are stress relaxation and creep. So I tried to include these. They were from the OITE website, and they're actually pretty good. They're just kind of small. If they ever show you a graph that has time as one of the axes, and it'll usually be the x-axis, they ever show you something that has time in it, that means that there is some relationship to the rate of stress or strain application. So they're trying to get at a viscoelasticity kind of problem. Creep and stress relaxation are exactly the same phenomena, but they're just measured differently. So on the left side boxes, the two on the left, on the bottom left, might be a little bit over engineering, but if you can understand it, it makes sense. So on the y-axis is deformation, another word for that is strain. On the x-axis is time. So this shows that if you put in a step of deformation, so if you take a tendon or anything that's viscoelastic, silly putty, a tendon, ligament, anything that changes shape as it deforms differently based on the rate of strain application. So if you take a piece of silly putty and stretch it 1 inch and you measure the force required to keep it at that 1 inch. So you put a step in deformation. So you stretch it 1 inch, which is a deformation or a strain, and then you measure the amount of force to keep it there. That force over time relaxes, and that's what they call stress relaxation. So you pull it 1 inch, and then you measure the amount of force that it takes between your fingers to hold it there over time, and it's probably pretty quick, on the order of seconds. That amount of stress to hold it there decays over time. So that's what they mean by stress relaxation. The exact same phenomena is responsible for creep, but it's backwards. So rather than putting in a step input, like putting in 1 inch of strain and measuring the stress or the force, you apply a constant force. So rather than stretching it 1 inch, you apply 10 pounds. So you have a step input in force, and then you measure the amount of deformation that comes out of that. So you apply 10 pounds, let's say you have a ligament over time, and all of a sudden you have one end that's fixed and you have another end that's hanging with a 10-pound weight or a 5-pound weight, whatever the weight is. And then you let go of that weight. Initially, it'll be very stiff because you've applied that step input in stress, or that step input in weight or force. But over time, if you were to measure the length of that ligament would gradually creep. So it's the same phenomena, creep and stress relaxation. One is an input in deformation or strain, and you measure the force, and the force relaxes, so it has force relaxation. The other is you have a step input in force or stress, same thing but normalized, and then you measure the amount of, you measure how much it moves, or you measure the deformation or the strain. Let's do Tyler Scott. If you had to explain stress and strain to your 12-year-old cousin, how would you do it?
Yeah, so stress, you know, to a 12-year-old cousin, that's be kind of difficult, Dr. Stacey, but
Yeah.
I guess just.
How about your 17-year-old cousin who's going to college?
Yeah. I guess if you have something, some kind of piece of material, you would just try to, you know, describe the force over area, but I don't know what kind of easier terms to be using that, but yeah, just the amount of force per area. So if you explain that to a kid, that's how I explain it. And strain is just.
How would you use the analogy of like a high heel versus just a work boot?
So a high heel, yeah, so there's more force per area than a work boot. So you have a bigger heel on the work boot. So yeah, there would be more stress on the high heel.
Yep.
And then strain.
The same person wearing a high heel, if they step on you, it's going to hurt quite a bit, right? Because you have however much that person weighs, 120 pounds, and then it's concentrated in the high heel area versus, like you said, a normal boot, same amount of weight, right? Same amount of force. But if it's distributed over a larger area, it has less stress.
Sure. And then strain, I would say maybe if you used silly putty earlier, so you could use silly putty as an example. So the amount of strain, if you pull harder, you know, the length would change more. So there would be more strain on the silly putty if the length changes more.
Yep. So stress and strain are just normalized force and deformation. So these two graphs up at the top, you could switch the axes. Rather than stress, you could put force. It's just not normalized, right? It's not normalized per area. And you could put, rather than strain, you could put deformation. Because in the real world, that's what you actually measure. You don't measure stress, right? You calculate stress. You can measure forces and you can measure deformations. So if you were in the lab doing an experiment, applying loads to tendons or applying loads to bones, you would actually be measuring a force versus deformation curve. And then engineers and scientists like to normalize things because depending on the size of the bone, right? if you're loading a femur, if you're loading a phalanx, you know, if you can normalize them to their cross-sectional area, force is a more meaningful engineering term than stress. Because, or I'm sorry, stress is a more meaningful engineering term than force, because it takes a lot more force to deflect a femur than it does a phalanx, but their stress strain curves should be identical because they're both made out of cortical bone, right? I know that's kind of complicated. I know that I wish I could do this in person, because this is one of those ones where having a whiteboard and being able to interact is very helpful to see how things behave on the stress strain curve. But just realize that stress is equivalent to force. It's just normalized by area. So its units are pascals or newtons per square meter, or pounds per square inch, something like that. And then strain, they normalize by the initial length. So you could say something displaced 2 centimeters, right? If that thing started off, whatever it was, if it was a bone and it displaced, if it was a femur and it displaced 2 centimeters, then you start with a 400 millimeter long bone and it displaces 2 centimeters. So you have to normalize it by its initial length to get a percentage of the deformation. So if it moved 2 centimeters and it started off as 40 centimeters, then it was a 5% deformation. Whereas if you had 2 centimeters of deformation on a radius, right? And let's say the radius was 20 centimeters long and it moved 2 centimeters, then you have a strain of 10%. Does anybody have any questions about stress or strain? Because it's hard to describe just with words, but I'm happy to try to do it with, next time you're here on a whiteboard or something. Feel free to ask questions about stress or strain is what I'm getting at. Anybody? No? Okay. Hey, Drew, are you there? Drew's not there.
Yeah, he's here.
Oh, Drew's here. Hey, Drew. They also like to ask questions about isotropy, however you say that. I don't know why, but tell me what, I don't know why they like to ask you questions about it, but tell me what an isotropic material is.
So isotropic is it's a material that has the same mechanical properties in all directions.
Right.
For example, like a golf ball, certain metals.
Yeah. Anything that if you apply a load to it, it doesn't depend on the orientation of what you're applying the load to. All right. So like, a golf ball, tennis ball, pool ball, anything that's homogeneous will usually be isotropic. Ceramics are, metals are. So it doesn't matter if you have a cube of metal and you're testing the material's properties of it, it doesn't matter how you orient that cube of metal. If you're pushing on it or pulling on it, it's going to give you the same results. What about anisotropic? What would an anisotropic material, what kind of materials properties would it have?
It'd be something that, depending on the direction of your force or applied load, it may, I guess, deform in a asymmetric pattern or.
Yep. So basically, I think of it as anything that has a grain to it, right? Like for wood is anisotropic, right? Anything that has something to it that would change the way it behaves based on how the manner in which it's loaded, right? Same thing with tendons. Tendons are a lot stronger in tension than they are in compression, right? You can't push with a tendon. It's really hard to push with a tendon. And you'll see, excuse me, like the trabecula in bone, like in the proximal femur, that's all of Wolff's law of how those trabecula have formed in response to the areas of maximum stress. Like in the proximal femur is the classic example, all of those stress lines and the trabecula line up. Most biological materials are anisotropic, meaning they have some grain to them, so it depends on the direction of loading. There's been a question on that, so I included it. They always like to ask you the other one, which is just the typical med school thing. They just want you to know which materials have the highest stiffness And I think there's a graph on OrthoBullets in terms of the stiffness of different materials, not only biologic materials, but also orthopedic implants. So who's over there? What's the stiffest, one of the stiffest things that materials they'll ask you about? TJ.
Hey, yo.
Is TJ gone?
This is DJ, ceramics.
Hi, TJ. Yes, ceramics is one of the stiffest. It's also very brittle. Right below ceramics, what's the next most stiff, I guess, is this easiest way to ask it. What'd you say? Did you say cobalt chrome? Good answer. What about Jason Kerner? Is Jason there?
This is Jason.
Hey, Jason's here.
Hi, Jason.
Hello. Are we asking what the next one is?
Yeah, we're in the next one. We got ceramic, we got cobalt chrome,
Stainless steel.
stainless, then titanium, then cortical bone, methyl methacrylate cement, polyethylene, like in total knees and total hips, then cancellous bone, tendons, ligaments, and cartilage. Somebody came up with a stupid mnemonic to remember that. What they want you to know, and the questions that I've seen, is that most of the orthopedic metals that we use, cobalt, chrome, stainless, and titanium, are all stiffer than metal. Ceramic is stiffer than all of them, but most of the orthopedic, did I say stiffer than metal? I meant stiffer than bone. Most of the orthopedic implants that we use are stiffer than bone. Cement is in between cortical bone and cancellous bone. And then tendon, ligament, and cartilage are the least stiff or the softest. Rather than remember the exact, I mean, I don't know if they would ever ask you if cobalt chrome is stiffer than stainless steel. Like, they would have to be very specific as to which, alloys those were and such. But if you can remember that all of the orthopedic metals, stainless, cobalt, chrome, and titanium, are all stiffer than bone, and ceramic is the stiffest of them all. And then PMMA is in between cortical bone and cancellous bone. And then tendon, ligaments, and cartilage are the least stiff. I think if you can kind of think of it in that way, I think you would probably have a 90% chance of getting whatever question they asked you about that. The other thing they like to ask about bending moments. So they like you to know that the stiffness of a plate is related to the thickness of the plate to the third power, and then the bending and torsional rigidity of a nail or a hollow cylinder is proportional to the radius to the fourth power. So sometimes they'll say if you double the radius of the nail, what does that do to the bending moment? And it's 2 to the fourth. What else? What else do you guys have any questions on whatsoever in terms of any materials properties, something you've seen, something, somebody told you when you were a med student that didn't make much sense? Now is free for all question time. Nobody has any questions? Drew, do you have a question? Or did you just?
What's that? No, I don't.
Oh.
Why does nobody use titanium implants? Like those striker plates, everyone's like, those are trash. Everyone uses stainless steel. If the titanium is closer to the modulus of bone.
Very good question. And we didn't talk about it much, but what other, so it's usually for, I think anything you're trying to get primary bone healing on, like if you can get direct, anatomic reduction of whatever you're reducing, And I think any sort of plate is probably would probably be okay in that scenario because it's just acting as a neutralization plate, right? It's not going to undergo much stress. It's not going to undergo much strain. Like you plate a clavicle, you plate a fibula, you plate a both bone forum. I think all of those would be okay with the titanium plate. Where I don't like titanium plates is anything where I'm trying to bridge a fracture, like a distal femur or something like that. And there's a materials property that we didn't talk about. That's a perfect question. So what material property of titanium don't most orthopedic surgeons like when it comes to bridging fractures?
Is it plastic deformation?
Nope, it's not a plastic deformation. It's usually more of a fatigue kind of thing. So fatigue is an interesting phenomena. If you take a coat hanger or a paper clip is the classic example of fatigue. I don't have a paper clip or a coat hanger, but you've taken a coat hanger before, right? And you can bend it once and you can plastically deform it so you reach its yield limit, but you haven't reached its ultimate tensile strength so it doesn't break, right? So you haven't fractured it based on the classic what we were talking about on this piece of paper, right? You didn't break it at up here. But if you do that again and you do that again, the same amount of force, right? You're not increasing, you're not going past the yield, or you're not going past the ultimate tensile strength. You do that same little micro motion over and over and over again. You do that 20 times or 50 times with a coat hanger, it's going to eventually break, right? Mm-hmm. Same thing with a paper clip. It's very hard to try it. It's hard to break a paper clip with one, you know what I mean? Take a paper clip and try to break it just with one cycle, right? In order to break a paper clip, you're going to have to do this 7 or 8 times to break it. The thing that people don't like about titanium implants is that they don't have a very good fatigue strength. So over time, when you're bridging something and you're relying on that entire plate, that, like you said, the distal femur or something you're trying to bridge, that whole thing is going to be flexing back and forth. Even the stainless plates have a problem with it. I've seen several of the Synthes stainless plates break it too. We like it for nails because it's very biocompatible. And again, the strength of a nail is proportional to the radius of the force. So you can make nails. You put a 12 millimeter nail in somebody. I don't think I've ever seen somebody walk on a 12 millimeter nail enough to break it. They might break their interlock, but they won't break their, who's that? You got a friend.
McGee.
Who was that?
I was on my phone earlier.
Oh, no worries. Oh, McGee, gotcha. So yeah, titanium is usually, it's very biocompatible and its modulus is closer to that of bone. It doesn't have great fatigue characteristics though. It also doesn't have great wear characteristics. It's soft, quote unquote soft, which is why they don't make like total knee components out of it, right? You don't want your femoral component rubbing on poly. You want a very hard, polished cobalt chrome, very smooth finish on anything that has a bearing surface to it. But that for like hip stems, total hip stems, most of them are a titanium alloy.
Okay.
They're very biocompatible. They have great ingrowth, right? So there's lots of benefits to titanium. I wish I had something that was, had the bony ingrowth of titanium and the strength of steel, right? So.
Yeah.
Good question.
Cool, thank you.
Yeah. What other questions you got? Any biomechanics questions you guys got? Nikki, do you have any questions?
No, not right now.
Okay. All clear as mud. So I think I'll ask you guys a favor. If when going through, I don't know how you guys are study for the OITE or study for anything, but I just basically had a notebook that I every year would break out and, revisit my notes on the subjects from the year before. Because after several years, I think have a pretty complete study guide. If you guys keep track of this, and if you notice any OITE questions or self-assessment questions on biomaterials that aren't on this piece of paper, if you add them and then let me know, because I think I think all of the OITE questions that are on ortho bullets now can be answered off this one piece of paper. So if you guys find something on there, or that you guys got us asked a question on that wasn't on there, let me know and we can add it.
That's awesome. Thank you.
No worries. So that's about all I had for biomaterials. What's you guys' next lecture?
Shoulder anatomy.
Oh, there's an SSSC.
Yeah, what's the SSSC? Anyone?
I got it.
Got it. All right. Well, if you guys don't have any more questions, I'm going to run down to the OR. Last chance.
Thank you.
No? All right.
Very
Y'all
good,
have a good day.
Thanks.
Oh, there's
Thanks,
busy.
Stacey.